So LTE stands for long-term evolution. And basically they have added the word E in front of everything. So EMTS is called EUMTS, evolution of UMTS. It has two parts, E ultra plus E utron. E ultra is the radio part and E utron is the terrestrial part. Right? That T is for terrestrial. Well, kind of confusing to me. But anyway, so LTE is the replacement for WCDMA, basically the wireless, the radio part. Right? And they are also changing the core network. The core network was whatever it was before, and I have a better picture later on, is now being replaced with what they call SAE. Actually, name SAE has been replaced as well, and it is called EPC. EPC is Evolved Packet Core. Evolved Packet Core, which is all IP packet core. Its original name was SAE. And in this case, all IP packet core, as I said, means that even voice is IP, so there is no analog voice, there is no circuit switched voice. This is designed for trial and deployment in 2010, which is this year, and I would really be surprised if we see deployments in 2010. I think trials probably will begin in 2010. There is no equipment. The standards just came out. They have to go through what they call conformance things, like WiMAX forum does conformance rules first. Multiple vendors get tested, and then you can do deployments. But this is what it was designed for. Frequency domain equalization, which is OFDMA. So, and there are four things which are quote new in LTE, and I say quote new because they're all there in WiMAX. And actually all the companies that worked on WiMAX are working on LTE, because what happened now is there are two camps, the data camp and the telephone camp. The data camp is the one that designed WiMAX. They go to IEEE, right? That is where the Ethernet was designed and so on and so forth. And Wi-Fi was designed. The telephony camp doesn't go there. They go to ITU. They go to 3GPP. So they designed LTE. And obviously there's the same company, same experts, same people. So, I mean, you can see 99% overlap, except there are few things which are different. Clearly what is different is that it is designed for telephony network. So anywhere there is any conflict, telephony people just make a decision in favor of their current technology, current business, compatibility and so on and so forth. Now there is no compatibility as such, as you will see. It's as compatible as IPv4 is to IPv6. That means dual mode. The phones right now are 4 mode, there will be 5 mode. But that's at least compatible in that way. So, so one thing, so there are 4 things, and I wrote them 4 here because number 1, 2, 3, 4, because this is what is the latest in wireless networking. And this is what is happening in all of the technologies that are being developed today, whether it is WiMAX or whether it is LTE. First thing is what we call OFDMA. The technical name for that is frequency domain equalization. The word equalization comes in the fact that if you have multiple transmitters, we said we have to equalize the volume, we have to equalize this and that. You can do that in time domain, you can do that in frequency domain. The way we do it in frequency domain is by doing this fast Fourier transform, and that is what we call OFDMA. Alright? So that was not there before, and so we had tough time doing equalization, and because of that we could not use big bandwidth. Like maximum that they could use in CDMA was 5 megahertz. With 5 megahertz you cannot go to 100 megahertz. Right? So if you want to go to any high speed data, you really need to do this wide channels, and for that you need OFDMA, so everybody is going to OFDMA. Second thing we do is MIMO, and I will talk about a little bit more about MIMO in this lecture. Third thing is channel dependent scheduling. So based upon the currently available, if it is raining, it's a different code than if it is not raining. If it is far away, it's a different code than if it is near. So that is what HSDPA did, that is what WiMAX did, that is what LTE does, right? And that is what everything else does. Dynamic channel allocation. Previously we had static channel allocation. So when you got on the phone, they gave you channel number 15 and that's yours forever. Right? You got a code number 15, that is yours forever. With dynamic means it is for this frame. Next frame you will get another thing. So basically we are sharing almost everything. Dynamic channel allocation. Okay. So that is LTE. So here's the thing, if I was giving a lecture on LTE, I would talk everything that I had talked in WiMAX because most of this thing is overlapping. I'm just going to talk about one or two items here because we have already talked about WiMAX, right? So let's first talk about the goals. It is designed, now these are the goals, not that you will get in the equipment because the equipment is not here yet and these are all the nominal numbers. So these are the best numbers basically as calculated on paper. You get 100 megabits using 64 QAMs ISO on 20 megahertz, which is actually 40 megahertz. So I have to do 20 times 2 megahertz. And 326.4 megabits using 4x4 MIMO. Uplink rates of 50 to 80 megabits using SISO. Scalable channel bandwidth. So that's another thing is previously the channel width were fixed. So if you had WCDMA, you had 5 megahertz, you couldn't have 3 megahertz, you couldn't have 7 megahertz. Right? Now they are going to use whatever they can get from 1.4 to 3 to 5 to 10 to 20. But you need times 2. And you can actually do times 1 too because it does TDD as well. Multiple frequency bands. Whatever band you get, 700, 900, 1800, just like WiMAX. Sub 5 millisecond latency for IP packet. Now, this is distinguishing factor. Why distinguishing? Because one of the reasons they asked us why do you need LTE, why not just WiMAX? They said WiMAX is not fast enough in latency, and the reason it is not fast enough in latency, suppose you get a packet. You have to tell the base station that I got a packet. That will take how long? The WiMAX frame is 5 millisecond long. They repeat every 5 millisecond, downlink, uplink, downlink, uplink, downlink, uplink, right? So first you have to find an uplink to tell the base station which is 5 millisecond, and the base station tells you that okay, you got the slot number 3, then you send the data. So there are already 3 trips, right? 15 milliseconds before the data made it there, right? That's too long. So what they did here is they did the frame which are 2 milliseconds long, right? So now you can do that in 3 round trips. Is 1 millisecond. You tell it, and next millisecond you come down, or something like so. Each something like that. So basically, this is less than 5 milliseconds. So this is one reason. Second thing is, and so there is one more related. So this is one major difference, right? It's not really major as such because all you did was the 2 millisecond frame is allowed by WiMAX, except that it is allowed by 802.16, but not really standardized in WiMAX. WiMAX group set 5 milliseconds. So anyway, then the distance, mobility wise, this is optimized for 0 to 15 kilometers, high performance up to 120 kilometers, and it will just work barely at up to 350 kilometers. After 350 kilometers, the performance is not guaranteed, working is not guaranteed. So can anybody guess as to what happens at high speed, what goes wrong? Doppler effect, and what does Doppler do to OFDMA? Each carrier frequency changes. Basically, you have the carrier here, and if you're moving, the carrier looks like over here, right? So it can overlap the other carrier, right? So there is inter-carrier interference. Compatibility with other cellular networks using multi-mode devices. Now this is all compatible with other 2G, 1G, 3G because your phone will have 1G, 2G, 3G in it. So then the cyclic prefix be changed depending upon the speed. Right? What is cyclic prefix? I need another slide to explain this thing, but let me just say basically cyclic prefix has nothing to do with mobility. What a cyclic prefix has to do with the reflections. Multipath. So what happens is, if something went there and came back to me, and something went very far away and came back to me, they come at different times. So there is what we call inter-symbol interference. If I had a bit which was so long, the second bit was here, but the first bit will overlap the second bit. So that is ISI, as opposed to what I just said was inter-carrier interference. So inter-symbol interference happens because of multipath. Right? Because in multipath there are different delays, and therefore we have symbols run into other symbols. Right? Now, to overcome that, what we do is we make every symbol longer. So what we do is, instead of having a symbol which was 1 microsecond long, we make it 1.2 microsecond long, and 0.2 microsecond at the beginning is same as the 0.2 microsecond at the end. That is called cyclic prefix. Because what we have done is we have taken the end, the tail, and put it in the front. So if there is any overlap, if somebody runs over it, no big deal, I still have another copy. Right? So cyclic prefix fixes multipath, and that is fixed, by the way. So that is not adaptively changed in any of the technologies so far, because that is one of the fundamental parameters. Just like we don't adaptively change the intercarrier spacing. So for example, in WiMAX the intercarrier spacing is 10 kilohertz. In LTE it is 15 kilohertz. That is not changed. Even so, basically we keep that fixed universally. So whether you use 1.4, 3 megahertz or whatever channel, this intercarrier spacing is 15 megahertz fixed. Right? Similarly, the cyclic prefix is fixed. So basically, WiMAX 10 kilohertz will allow you to have only so much error in your frequency spacing. Right? With 15 megahertz, now the carriers are a little bit farther away, so you have more room to move around. At high speed, what will happen is you will have Doppler, you will have intercarrier interference, and then what will happen is your data error rate would be higher, and so your effective rate would be very low, to the point where it will become zero if you're running at 350 kilometers per hour, and then sorry, your error rate is 99%. I mean, it's not that 15 kilohertz means there is no interference. There is interference, even with that spacing, but there is less. If it was 10 kilohertz, there will be more interference. That's what I said. This is one of the fundamental parameters, so it is not changed dynamically, not right now, maybe next year. Okay? I mean, right now it is just too complicated to make devices that have. So just like I said, cyclic prefix is not changed, carrier spacing is not fixed. So there is a whole set of parameter values that we specify in our WiMAX papers, remember? Those are basic parameters, we don't change them. Even, for example, the frame size is variable, right? I mean, why don't we change the frame size? Not in 16E, but in 16M, yes. So maybe the next version may have it variable, but not in this version. So by the way, 16M, when we talk about next time, you will see that they have changed, that they have taken care of many of these issues, because these are the same people. They go there and then they come back here and they say, wait a minute, we need to change it here. So they are just following each other. Alright, so CDMA versus OFDMA. CDMA versus OFDMA, I think we have discussed most of it, but just want to one more time repeat it. If you want to be frequency selective, means that that there is a noise which is in this zone, and you want to take care of it. It is much easier to do with OFDMA. It is not possible to do with CDMA, because even that one frequency, if you have 5 megahertz channel and you're using the whole 5 megahertz in CDMA, the frequency selective effect noise will affect you. So there is no solution. Symbol period. The bits are very short. Actually, the bits are shorter than the bits itself, the chips, because instead of bits, we transmit chips in CDMA. So there is a lot more symbol interference. Well, it's not symbol interference, it is chips interference. Symbol is that big, by the way. Each bit is a symbol, right? So, or it could be even more. So, So the symbols are short. Here the symbols are very long because we have only 10 kilohertz. So that's the advantage of having 10 kilohertz. 10 kilohertz symbols are so big. 15 kilohertz symbols are smaller. All right. As you increase the width, the symbols become smaller. And that's the whole purpose of OFDMA. The OFDMA, the basic principle is that we don't want to use this much bandwidth. We want to use only this much. With this much bandwidth, the symbols are so big. Each bit takes longer. And that's the whole idea of OFDMA. So there is a trade-off between 10 and 15 kilohertz, and the trade-off is mobility versus multipath. Big symbols are good for multipath, but small carrier interspacing is bad for high speed. You see, so either you go high speed or you go multipath. One of the two. And so that's the kind of trade-off you have to make. Equalization. This is equalization works only up to 65 megahertz, and this is for any bandwidth. So now we are talking about 100 megahertz. Okay, very wide channels. Resistance to multipath. This is very difficult to do with CDMA, and this is possible to do with proper cyclic prefix. This is what we were talking about. The cyclic prefix is that repeated part. MIMO is very difficult to do with CDMA. It's very easy with FDMA. Frequency distortion is averaged. This causes inter-carrier interference. So that is what the problem actually is with respect to motion. OFDMA is not good for motion. Then user multiplexing you can do by having orthogonal codes. Here you can do in frequency and time. All right. So with that, we know why CDMA is going away, why OFDMA is coming in. Now there is a second change that the LTE people have done, which is not in WiMAX, is single carrier FDMA, SCFDMA. SCFDMA. And the reason they have to do that is because OFDM, each carrier is modulated according to specific channel conditions. So you have these 1,000 subcarriers. One has BPSK and one has COM64, right, depending upon the condition of that particular carrier. Because of that, there is a big variance between the minimum and the maximum. There is a big difference between the peak and the average power. And that makes the amplifier design very difficult. I think we talked about this earlier, right? Peak to average power ratio, if you get an amplifier, they are, by the way, the most expensive part in the whole system. So when you design a UE or a base station and you get the power list, part list, and you get the cost list, the highest cost is amplifier. And I have done that because at some point I was trying to design some product. So highest cost is amplifier, and if you use, so according to them, if you use this high pepper thing, then it will be even more expensive because the amplifier has to operate linearly in this range as opposed to in this range. Right? So how do we reduce the pepper? We use single carrier. With single carrier, the peak to average is very small because single carrier, right? So how do we do single carrier? Basically, what we do is we take the symbols that we want to translate. So these are in time domain. We send through a what we call discrete Fourier transform chip, which is M by M. That comes out in the frequency domain as M frequencies, M carriers, M subcarriers. Right? This is discrete Fourier transform. What does Fourier transform do? Translate from time to frequency or frequency to time, right? So it comes out M. Then we do a inverse discrete Fourier transform, which is N by N, and we connect these M to some M symbol. It doesn't have to be any middle M or anything like that. This could be any M value out of N. Right? That comes out in time domain again now. So this was in frequency time, this is in frequency domain in the middle here. See, it says subcarriers. Right? Now after inverse it becomes time domain again. Now we do all that cyclic prefix and whatever we need to do, and depending upon where we connect this spectrum will be either here or in the middle or something like that, depending upon where you connect these pins. All right. Now, so this actually, when you see here, this looks like a single carrier, because this whole carrier is totally used. But the way we got this single carrier is by doing a Fourier transform and inverse Fourier transform. Right? Now, if you didn't have single carrier, then all we do is we take this and we convert into a n by n discrete Fourier transform, right, for OFDMA, and we connect all of the pins to all of the pins. Right? In that case, you get the subcarriers here, and then you get this kind of. So basically, so the idea is that instead of having this full DFT, we have a small DFT. So this is called DFT pre-coded OFDM. This is called DFT pre-coded OFDM, because before we went to the OFDM part, we had DFT pre-coded, right? So M by M DFT is used before M by N IDFT, where M is much less than N, and results in a waveform that is similar to a single carrier, and therefore it has 1 to 2 dB less pepper. So when you talk to WiMAX guys, they say, hey, there's no difference, man. Come on, 1 to 2 dB for which, why we have to make such a big deal about it? But you talk to LTE, oh, that makes a big difference. That's the key. Okay? So that's the debate going on right now. Whether this change is worthwhile or not. Why don't we just take the WiMAX standard and take the chips and start making it for cell phone companies? But they say no, this single carrier makes a big difference. That frame size of 2 milliseconds makes a big difference. But those are the two major differences. So MIMO, I just wanted to add some more information about MIMO before you get out of this wireless class. And so you already know SISO was single antenna, right? And MIMO is multiple antenna, both sides. So this is single user MIMO. Why do you call single user MIMO? Because each user has to have multiple antennas. So how do you put 2 antennas on a tiny cell phone? And they have to be divided a quarter wavelength or half wavelength apart. And if the wavelength is 700 megahertz, the wavelength is so big, you need to carry a kind of an antenna with you, like an umbrella or something. So that doesn't work, right? So then they invented what we call multi-user MIMO, where you need 2 antennas, but they don't have to be on the same equipment. They could be on 2 different users. And the way it works actually is, because the way it worked in the previous single antenna was that we had this matrix, carrier versus time. These are subcarriers. Here are shown 4 subcarriers and 4 symbols times. And we use some of these combinations for pilot. These are the reference symbols, where we figure out if I'm sending you this here, what you are getting, whether the channel is good or bad. So we put the pilots, right? From the pilot we can tell the condition of the channel, right? So these pilot positions tell us, when you have MIMO, then the pilot positions tell us which of the signal is which path, following which path, and we can actually get a very good idea of what we call the channel matrix using these pilot symbols. Same thing happens here. Now when we are sending these to these, we tell one user to put the pilot here, XX, and put other user to put the pilot YY. When we receive, we can get a good idea of the channel matrix, and we can separate out the 2 users. And so that is called multi-user MIMO. Multi-user MIMO means user only has 1 antenna, but there are multiple of the users, therefore they have multiple antennas. All right. Then there is called cooperative MIMO. Cooperative MIMO is doing the same thing, but doing on the tower side. Instead of having 1 tower have 2 antenna, which is much easier to do. It's no big deal to put an umbrella on a tower. But if you use 2 towers to transmit, then you got a cooperative MIMO. These 2 towers are collaborating to reach you. Right? So this is another kind of MIMO. All of these modes are allowed in LTE. And if they're allowed in LTE, they're also allowed in 16M. They may not be allowed in 16E, but they are allowed in 16M because 16M came after LTE. So this is the thing. First came 16E, then came LTE, then came 16M, and then coming LTE advanced. Alright, LTE version 2. So the LTE version 2 will have everything that is 16M plus more. So there is a repetition of all of these things, and this is a nice debate in the industry. So this is basically, this slide simply shows the complete description of the 3.5G. So you have 2G systems which have the BTS and BSC and then MSC and gateway and all that, and this is all circuit switched. CS core means circuit switched core. By the way, this slide goes with the next slide, which has all the acronyms. And then when we had 3G, in 3G we added the packet switched core as well as circuit switched core. The voice went through the circuit switched, the data went through the packet switched part. Now in 3.5G and 4G, first of all, this RNC is gone. So we have E and B, which does the whole thing. And second thing is that everything is packet. This is called Evolved Packet Core, EPC, Evolved Packet Core. This whole thing is called Evolved Packet System, EPS. All right? So that's all I wanted to say. So basically, so the idea is that we have finished now all about 3.5G.